stoichiometry, trying to figure out how much product you would get if you're given a certain amount of reactant, or how much reactant you would need to give you a certain amount of product. What do you do, though, when a question gives you two different starting points? We end up with something called limiting reactants or limiting reagents. So before we get into chemical examples, let's try something that you can picture in your head a little more reasonably. Let's think about making a ham sandwich. Suppose you've got 7 slices of bread and 3 slices of ham. And you know that you're going to make sandwiches, and you need 2 slices of bread with a piece of ham between them. How many sandwiches can you make? And will you have leftovers? And how much leftovers will you have? Well, very quickly, most of you will realize that you can make 3 sandwiches and you're going to run out of ham. You'll have a slice of bread left over. In your head, whether you realize it or not, you are doing limiting reactant stoichiometry. What we have here, for example, could be considered a balanced equation for the making of a ham sandwich. In the equation in blue, I've written this as if it were a chemical equation. We know that 2 breads plus 1 ham makes 1 sandwich. This would be an equivalent of a balanced equation in chemistry. The example underneath shows not how much we actually reacts together, but how much we actually have. We don't have 2 breads, we have 7. And we don't have 1 ham, we have 3. Now, really simple math in your head lets you know, because you can see it quite clearly, that the ham will get used up first. You knew the ham was going to run out, and because you knew the ham was going to run out, you said, well, if 1 ham makes 1 sandwich, then 3 hams would make 3 sandwiches. Most of you didn't start with the breads and try to turn that into what was going to be the amount of sandwiches. You used the thing that ran out first. That is called a limiting reagent. When we have chemical equations, when we have 2 different starting points, our first job is always to figure out which one is going to run out first, and then using that number, we can determine how much product will actually be made. This is a similar example with a common chemical equation. We know that 2 moles of hydrogen gas reacts with 1 mole of oxygen gas to make 2 moles of water. But what if we have a container that contains 10 moles of hydrogen and 7 moles of oxygen? How much water gets made? Which one of those runs out first? Will there be leftovers? And how much will be left over? How do we set up this type of question? Start as always by writing out your balanced equation. This shows the minimum ratios that things will react in. Now we consider our actual starting points. We have 2 different starting points to choose from, 10 moles or 7 moles. The way that we go about approaching this problem is to try both separately and see which one will make less product. We'll start by mapping out both pathways. We know we're going to try going from the amount of hydrogen to water, and then in the second step, going from the amount of oxygen to water. Let's start by solving using 10 moles of hydrogen as a starting point. I've decided to label this line in green so that we can see the 2 separate sets of calculations separately. We know that we're at 10 moles. Remember, moles always gets labeled on the corner of our little diagram. The endpoints are for grams or for liters or number of particles. We're going to start with the 10 moles of hydrogen, from which I can turn that into moles of water, and then if I need to, into grams or liters of water. In this case, I'm going to end up stopping at moles of water. It doesn't really matter where I stop, so long as I pick the same stopping point for both lines. Because my factor label line is only going to use 2 points, or my diagram only uses 2 points, my factor label line will only have 2 seconds. Stop with what you know. We're starting with 10 moles of hydrogen gas. So here I write 10 moles of hydrogen gas. I want to get rid of the words moles of hydrogen gas, so I write those on the bottom. Remember to leave a space for the number. Where I'm trying to go is to moles of water. It's what I want, so I write that on top. Now we need numbers to make it true. When we have a moles to moles section on the factor label line, the numbers that we use come from the balanced equation. In the balanced equation, there's a 2 beside hydrogen, so I'm going to put a 2 beside hydrogen here. And there's a 2 beside water, so I'm going to put a 2 beside water there. Now, moles of hydrogen on the top cancels moles of hydrogen on the bottom, and we're left with moles of water. Doing the math, 10 times 2 divided by 2 gives us 10 moles of water would be made. How would this be different if we started with oxygen? Again, we're going to start with what we know. What we know this time is that we are at 7 moles of oxygen. We are here. We're trying to find out how many moles of water would be produced. Starting with what you know, that I have 7 moles of oxygen. I want to get rid of the words moles of oxygen, so I write them on the bottom, and I'm changing it to the words moles of water. I write this on top. Moles to moles comparison, the numbers come from the balancing. In the balanced equation, beside moles of water is a 2, so beside moles of water, I write 2. In the balanced equation, in front of the oxygen, even though we don't see it, is the number 1, so here I'll write a 1. We now see that the words moles of oxygen on the top cancel the words moles of oxygen on the bottom, and 7 times 2 gives us 14 moles of water vapor. If I start with the hydrogen and use it all up, I can produce 10 moles of water. If I start with the oxygen and use it all up, I end up being able to produce 14 moles of water. Clearly, I don't have enough to produce 14 moles of water. We've already shown that if I use up all the hydrogen, I've only produced 10 moles. There's not enough hydrogen left to make 14 moles. Because the hydrogen gets used up first, it is called the limiting reagent. The oxygen will have more than we need. Because the oxygen will have more than we need, we will call it the excess. Once we've determined which one is the limiting reagent, it is the number we use for all future calculations. We know hydrogen runs out first, so only 10 moles of water will be produced. We have now calculated how much water we'll get. We know we're going to have leftover oxygen, but at this point we don't know how much. To figure out how much oxygen will be left over, we have to do one more calculation. This time we're going to say, because we know all 10 moles of hydrogen gets used up, we're going to go from the moles we actually have of hydrogen, which we remember to label on the corner of the line, and we're going to use our stoichiometry to figure out how many moles of oxygen we actually will use. Starting with what we know we have 10 moles of hydrogen that will get used up. Because 1 mole of oxygen reacts with 2 moles of hydrogen, we'll use the 1:2 ratio from our balanced equation. We see that 10 divided by 2 will give us 5 moles of oxygen will actually get used. If we have 7 moles of oxygen available, but only 5 moles of it get used, we'll have 2 moles of oxygen left over. Using limiting reagents is the same skill set that we used for all stoichiometry calculations. The starting point, however, is to try both given pieces of information and determine which one gets used up first. Once you have determined the limiting reagent, use that number as the starting point for all other calculations. Once we've determined the limiting reagent, the other number is just there in excess. There's more than we need, so we don't use it to start any other factor label lines. Let's do one more quick example. In this example, rather than being given moles, we're going to start with grams. In this example, they say that we've got a strip of zinc metal and we've weighed it to weigh 2 grams, and we put it in an aqueous solution of silver nitrate, which weighs 2.5 grams. We're going to get a reaction. It's going to produce silver and it's going to produce zinc nitrate. The question says how many grams of silver will form. It doesn't matter if they ask how much silver we're going to get or how much zinc nitrate we're going to get or both. We're going to have to try both starting points, making sure that we compare them to the same product to see which one produces less. We can compare both of them to find out which one makes less silver, or compare both of them to find out which one makes less zinc nitrate. Either way, make sure that you're comparing the same product. You don't want to be starting with zinc and going to silver in one case and starting with silver nitrate and going to zinc nitrate in the other. You want to make them have the same endpoint. It's the only way you can find which one runs out first. Because this question specifically asks for silver, we're going to try both starting points to see which one will make less silver. So once I have my balanced equation that tells me the ratios they act in, I'm going to start by considering my two starting points. I have 2 grams of the zinc. I have 2.5 grams of the silver nitrate. What we're interested in is how many grams of silver we're going to get. As always, I start by mapping out the pathway I'm going to follow. We're going to have to do 2 separate factor label lines because we have 2 separate starting points. Let's start by considering, if I start with grams of zinc, how many grams of silver would I produce? Because we're starting with grams, I'm going to label that on the end of my line. We're going to first change grams of zinc to moles of zinc. We will then go from moles of zinc, following our line, to moles, always moles on the corner, of silver. And finally, I'm going to carry this on one more step to find grams of silver. Now, for the point of comparison, I could have stopped at moles. I could have done a shorter factor label line and saved myself one step, as long as I also stopped at moles when I started with the silver nitrate line. So I'd be comparing the same thing. But because the question eventually asked me to find grams of zinc, it is convenient for me to solve for that now. Our factor label line has 4 sections, so we're going to set up a 4-section factor label line using each corner as the top part of our line and solve for grams of zinc. Starting with zinc, if we start with 2 grams of zinc, using the molar mass, change it first to moles. 1 mole of zinc weighs 65.38 grams. Then, using the balanced equation, change moles of zinc to moles of silver nitrate. Oops, got that one there. We're actually going to grams of silver. So 2 moles of silver is produced when 1 mole of zinc reacts. And then using moles of silver, change it to grams of silver using molar mass. Every 1 mole of silver weighs 107.86 grams. Again, you don't have to use a 2 here. The only place we use the numbers from the balancing are in this moles to moles ratio. Multiplying numbers on the top of the line and dividing numbers on the bottom of the line gives us 6.6 grams of silver would be produced if I used up all my zinc. Let's try this now using our silver nitrate as our starting point. Following along with our second given information, if we start with this 2.5 grams of silver nitrate, which I label at the end of the line, I could change that first to moles of silver nitrate, and then using my balanced equation, change that to moles of silver, and then using the molar mass, change that to grams of silver. Starting with 2.5 grams of silver nitrate. We know that 1 mole of silver nitrate, each 1 mole weighs 169.87 grams. From the balanced equation, 2 moles of silver reacts with every 2 moles of silver nitrate. And to change that to grams, there are 107.86 grams of silver for every 1 mole of silver. Multiplying numbers on the top and dividing the numbers on the bottom gives us a value of 158 grams of silver, or 1.58 grams of silver. Clearly, if we start with the silver nitrate, we get much less grams of silver produced. Once we've produced 1.58 grams of silver, there is no more there's no more silver nitrate available to react with the remaining zinc. So only 1.58 grams will be produced. In this case, silver nitrate becomes our limiting reagent. If I now was asked to find out how much zinc nitrate was to be produced, I don't have to try both again. I would just start with silver nitrate, the 2.5 grams, and change that amount using my factor label line into zinc nitrate. I go from grams to moles to moles to grams. I would do one more factor label line. If I wanted to find out how much zinc was left over, I would change grams of silver nitrate used into grams of zinc that we actually used up. I know I'd use up all 2.5 grams, so again I'd go grams to moles to moles to grams. Again, I do another 4-point factor label line. And the amount that was used, I'd subtract from the amount I had. Again, once we've determined the limiting reagent, it becomes the starting point for all future calculations. It's not any more difficult than what you've been doing, it's just a lot more work. From this video, I'm hoping that you can determine which reagent will be limiting and which will be excess. Once you've determined that, can you determine how much of the excess gets used and how much remains? And can you determine how much product will be made? There's lots of practice available for you here on workbook pages 46 to 49. On these pages, you get lots of practice with regular stoichiometry, but also because there's more than one possible starting point, you're also practicing understanding of limiting reagents.